All right, so we're starting to get on time. So this is a slide-heavy presentation session for today. I will not be doing any demos. It is a comparison between the different or 4 different vendors in an area. So I might have some oversight. There might be nuances that I don't touch about, but if there are any questions or any comments, feel free to raise them during the session or afterwards in the questions period. So my name is Johan Ludvig. I'm Norwegian. I work for Capgemini in Norway as a solution architect, and I'm also a Microsoft MVP for data platform. Today I'll be talking about the battle of the cloud data warehouses. It is an oversight session, so we will start on a very low level to look at what came before, what led up to these cloud data platforms. So we'll be talking about data lakes and data warehouses, the battleground, the opponents, and then I'll do an analysis of the different opponents and my opinion on who won the battle. So the enterprise data warehouse has been around since around about 1988. Back then they called it the business data warehouse. It has evolved over time. So there's even though you can recognize a lot of the things that was back in 1988, there is still plenty of new stuff as well. You have 3 main approaches to the data warehouse solution. It's the dimensional approach, or Kimball. It's a normalized approach via Inman, and it's Data Vault, or Data Vault 2.0, which is the current version of that, which is more of an open source organization than coming out of single person or single institute, so to speak. So the enterprise data warehouse is subject oriented. It is integrated, so it tries to connect all the different sources within an enterprise, and then make them align them across, so it's easier to query the different sources. It is time variant, so it looks at changes over time instead of what is happening right now. It is non-volatile, so we want to delete as little as possible. We want to update and show changes again over time. And it is summarized, so we're looking at aggregated figures. There is, of course, always a grain, so then we're the lowest level of the grain in the warehouse, but we're looking at summarizing figures and having as exact sums as possible. And enterprise data warehouse, of course, we're dealing with a relational database, so it is structured, and it is schema on write. We push data into schemas. It is a relational database. It stores historical data, and because it stores historical data from sources, several sources, it needs to be transformed. And typically we transform the data before we store it in the data warehouse, but you might see variants of somebody raised their hand. No, okay. So you might see variations of staging areas or operational data stores and so forth with raw data, but you store data in the data warehouse itself after it has been transformed. And it is very good for business decisions, whereas it's not as great for showing trends and what might happen, so to speak. Data warehouses also focus a lot on data quality and focus on the exact numbers, because again, we're talking about enterprise-wide decision-making, seeing how the business is running, why, if sales are dropping, why they might have been dropping. And these numbers need to be exact, so you need to have a long development cycle to make sure that all the data that you present in your reports are as close to the exact truth as possible. But because of the way that the data warehouse has long time to market, it has a lot of challenges with data quality and development cycles, combined with the constraints that are in a relational database and schema on writes when we are looking into the big V's of big data, so volume, variety, and velocity, or you might even have more if you want, but I'll stick to these three. The data lake tried to answer a lot of these problems that face the data warehouse. So around about 2011, it gained foothold. You have the raw data lake, which is where you store data as is. And then, of course, you have what they call a business data lake or a layered data lake as well. And the main principles of a business data lake is you land all the information you have into your raw layer as is with no modification. And you encourage line of business to create point solutions. So if the marketing wants data to deliver to their reports, they make line of business or line point solutions for their specific needs and nothing else. And that means that IT can free up time to let business decide on cost performance. They can concentrate on governance for the critical points only. And in this aspect, in a data lake, the enterprise or the corporate view, which is what the data warehouse delivers, is just another line of business. And in a business data lake, any information is information, whether it is structured or unstructured. But you try to take, even though you try to take in everything, you still look at the lake as not full. It doesn't contain all information. And in a data lake, scale is driven by demand. So you need to have scaling both up and down, versus in an enterprise data warehouse where you're more stuck in a pre-configured scaling system. And a data lake in its basic form is a repository. So it's where you dump all your data that can be blobs or files. It is schema on read. You don't care what the schema is in until you start querying the data files. And because you store any kind of format, it means that you can both have unstructured data, or CSVs, JSONs, XMLs, but you can also have relational databases in the data lake. And you try to store all the data that you can. And the raw layer is, again, no transformation, as close to the source as possible, because the transformation will happen at later layers and later stages in the data lake. And various use cases and various users have different needs and different access to the different layers of the data lake. So typically you want to see analysis data scientists or advanced analysts and data scientists and data engineers accessing data in the raw layer or even in the staging layer, whereas end users and regular business analysts typically look at data in a curated layer of the data lake. It is great for trends and for ad hoc analysis. And because it focuses on line of business only and it focuses on trends and ad hoc, it means that it has a lot shorter time to market development cycles, because you don't need to think about what the numbers are as you push them out. You don't have that much quality controls built in. And the data lake is a great enabler to data science projects and to self-service BI. However, because you want to store all the data that you can, and typically, at least in an IT fashion, a lot of us are saying, okay, we might not have any use for this keyboard right now, but at some time this one will break down and it's nice to have a backup. So the same principle also applies to data. I might not need this data right now, but maybe in 10 years time I'll need it, so I'll store it in here anyways. And in the end you end up with a data swamp. So you have too much data in, you have no control of what data is there, and in the end it just costs you money, because data that you can't analyze and don't analyze will just be a cost center for you. And the cloud data warehouse initially was a response to the challenges faced by a traditional relational data warehouse, where they introduced parallelism. And in the cloud setting, it is a massive parallel processing engine, but it's still an enterprise data warehouse take with the same kind of constraints on development cycles and time to market. And the battleground for our cloud data warehouse setting is, of course, the cloud. Because, again, the initial take of the cloud data warehouse was to take over and try to alleviate some of the pains in your traditional data warehouse. But there are so many different use cases, data science, self-service, and so forth, that is very alluring with the data lake. So can we somehow merge these two aspects of enterprise data analysis into one? And there are several approaches to this. Of course, you have the Gartner construct of your logical data warehouse, which until recently has been a bit difficult to implement. You have virtualization such as Denodo or TIBCO, which is very tempting on paper. It has lots of nice features, but it will always be as slow as the slowest data source, unless you start building in functionality as caching and temporary storage and so forth. And then you're getting back into a data warehousing kind of solution with the need for technicians and the need for data, for hardware and so forth to actually get that caching mechanism working properly. And this is the battleground where the cloud data warehousing solutions come in. And the opponents, I see I forgot to update one logo here, but you have Azure with what is now Synapse, but previously SQL Data Warehouse. You have AWS with Redshift. Google has its BigQuery, and then there's the independent player Snowflake. And Redshift is a massive parallel relational database system. So it is based on Postgres in the same way that SQL Server is based on, and my mind suddenly failed me, but it's it also based on the system, and it all evolved over time. So even though they still have some similarities, it's a completely different system. Redshift is a columnar database. For those of you who are familiar with the SQL Server and column store is a columnar way of storing data. And it has nice compression features. And this also helps speed up certain kind of queries. The massive parallel architecture of Redshift is set up with distributed databases, which means that it has a controller node and then several compute nodes underneath, where it has copies of each database lined up over the various nodes that you have in your system. So it distributes that data across databases within a cluster. And the different distribution types of data in AWS is on key, all, or even. And this means that you can either distribute on a certain customer key, it can be year, it can be something else to partition your data on. You can put all data into one database copy, also that means one node. Or you can do a round-robin even distribution of all data across all the different nodes in your cluster. And Redshift has 3 different versions in the market right now. You have dense storage, which is the oldest version, means that it has a focus on storing lots of data, but it has not as much compute power. It's a bit slower. Then you have dense compute, which is a bit more expensive, but has a stronger compute. And then you have the Aqua, or Advanced Query Accelerator, RA3, which is the latest version of Redshift. And this is the architecture of the dense storage and dense compute version, where you have a leader node, and then you have compute nodes. And within each compute node, you have compute slice and storage combined. So Redshift DS and DC versions do not have separate storage and compute. They are bundled together, so they will be always on. Then last year, Redshift introduced the RA3, which is an attempt to then compete against the different architecture of SQL Data Warehouse and Snowflake, where you have separation of storage and compute. So it still has that leader node where all queries hit against, and that distributes the compute to the different compute nodes. But underneath there you have managed storage, which is separate from the compute nodes, and that storage is both in SSD disks and S3 buckets underneath. So typically Redshift will analyze the frequency of data being used, and it will shuffle out data that is not frequently used and dump that into cold storage and S3 buckets, which allows for better price performance on storage. But of course, if you are querying against that cold storage data, there is lag to get that data out to you compared to the ones that are in hot storage. Yeah, so it's a bit, sorry for this, it's a bit different to go through my slides when it's been stored on Avatar Land and having it shared on my screen, so that's why I'm not always seeing what I thought I will see. Anyways, Redshift Spectrum is another service as part of the Redshift portfolio, and that is an ability of Redshift to query data that is not stored within your data warehouse, but stored externally on your data lake. And this allows you to, within your Redshift SQL Query Studio, you can query against external tables all the data that is in the S3 buckets that are shared with Redshift. And this leads you to be able to pull data in that has been either downloaded ad hoc, or it has been downloaded but not transformed into Redshift yet, in a fashion that is seamless. Okay, there is a lag again to pull that data in and make it available for you in Redshift. But for those of you who know SQL Server better, you will recognize this feature as pretty close to what Polybase version 1.0 was. So querying over a blob storage for files. And then you can build materialized views on top of that. So you pull that data from the CSVs or from the blob files into your Redshift SQL and have that data available in SQL in materialized views. So it's a very quick and easy way to build closer to what a logical data warehousing solution might be without having to go through your traditional ETL pipelines. So the other competitor we're looking at today is Snowflake. And Snowflake is a pure cloud platform. And since my title is Cloud Data Warehouse, why do I say Cloud Data Platform? I'll come back to that in a bit. But it is built for the cloud, been around since 2012, 2013, something like that. It's based on ANSI SQL. So it's, again, pretty familiar if you know SQL code. It is columnar as well. It has separated computes, and these compute nodes are called warehouses. And then storage is separated, but shared among the different warehouses. So all warehouses in the system can access the same databases. And it is what they call maintenance-free, in that you don't need a DBA because there are no indexes on the system. The system itself maintains all indexes it feels it needs. It analyzes the query patterns and then creates ways of handling and speeding up those queries as they come along. But of course, maintenance-free is marketing lingo. You still need to think about, if you write shitty code, you will write shitty code, and there is no way to improve that. Apart from paying Snowflake more money to use bigger compute nodes. Snowflake architecture is a bit similar to the rest in that you have on top, see if I get that right. No, that was, sorry. You have your common services on top. So you have IAM, so authentication, access control. You have transactional manager. You have your query optimizer and security layer. Then you have metadata storage that is common among all the databases, which again is why that it allows for a shared data storage across the nodes. The metadata is separated. Then you have your compute nodes, which also has a hot cache. And that cache is persisted as long as the compute nodes are running. And underneath the hood, you have your shared storage. And that storage is here shown as a database. You can have multiple databases shared as well. That's not an issue. And Snowflake, as an independent provider, has connections to all the main hyperscalers in the cloud. So both Google, AWS, and Azure are available as cloud platforms for Snowflake. Just one more note on that is that Snowflake does not run in Azure, does not run in AWS. It runs on a separate instance or a separate data center that in a shared environment with the different providers. So for Azure, that means in Western Europe, you have Amsterdam and Switzerland, I think. Whereas AWS is London and Dublin, and Google is, I can't remember with it. It has only a few localities, which in a GDPR perspective might or might not be an issue for you. I know in Norway, there are certain, at least government organizations, who exclude Snowflake due to this constraint that is in here. Right, so the Snowflake architecture in a use case setting means that you can have different compute nodes dedicated to different use cases or different departments or different teams. You have several sizes of compute nodes that you start with, from extra small to XXXL. And they are scalable automatically. So you can start off with an extra small service for the marketing department and their click reporting. But you can set that so it scales upwards, or let's say for finance, you have an extra small for finance, and during their monthly reporting, you allow them to automatically scale up to large, or even extra large if that's needed. So it can handle the extra load on the monthly reporting, and then scale down back again to extra small afterwards. It also has an auto pause option, which is quite nice in that you can set Snowflake to auto pause after 5 minutes, 30 minutes, an hour, or when it has not had any queries against it. It flushes the cache, but it means that you don't pay for the compute power as long as the warehouse is paused. And it goes from cold to hot within minutes. So it's really easy to start it up again when the user starts hitting that compute node again. So this means that you can have lots of warehouses dedicated. So you have your small one for ETL and data warehousing solutions. You have your large one for data science. You have your small one for finance and marketing, and so forth. And you only pay while it is running. So, and you don't pay for the number of instances you pay. I think it's the way that they're pricing this is you start at 1 credit for an extra small one, and then the small one is 2 credits and the large one is 4 credits and so forth. So it's quite easy to calculate the costs in this way. And because the data is shared and everything is in one environment, even though you have several compute nodes, when you want to have a dev or test environment, you can just create a copy or a clone of your production database and attach that or connect that to your your test dev compute node and have a separate instance running. And that cloning option is really, really fast. We're talking about minutes to get the clone up and running for test uses. So Snowflake can query over data lakes. As I mentioned, it has connectors to all the main cloud providers. So you can have your data land in S3 buckets or in Azure storage, and then Snowflake can automatically pull that data in as external data. Again, same thing as with Redshift, you have your external tables, and then you can quickly build materialized views on top of that. However, when you start building materialized views on Snowflake, that incurs a separate cost because it maintains them. So even if you build a materialized view on top of tables, and when these tables are updated with new data, the materialized view is also refreshed. So that's why you have that maintenance cost on them. As to why Snowflake is a cloud data platform, well, you have all the different source systems that you want supported. You can support pull data in via batch. You can pull data in via CDC, ETL pipelines, real-time streaming, IoT. Either go through your cloud provider of choice, or push that data directly from your local systems into Snowflake using systems such as Fivetran or Matillion or something, and land that in your databases within Snowflake. It is very easy to work with XML and JSON and CSV files in Snowflake as well. Then you have your data lake support over external tables. You can do data engineering in Snowflake by building snowpipes to pull data and transform data in. Of course, it supports features such as stored procedures and so forth as well in Snowflake, as with any other databases. Then you have a data exchange, and that data exchange is two separate features. One is that you can share a set of data or even a database copy with partners, with providers, with customers by slicing off a data set and then inviting users in to read and access that data. And you can share that data via Snowflake user. You have to have a user here. I haven't tested this with Azure Active Directory because you can set up Azure Active Directory and Snowflake to sync automatically. But they need to have a user in Snowflake to be able to access that data share. However, the data exchange is also public in that it's you can monetize and sell your data on a data exchange within Snowflake to other Snowflake users. So it's a way of enabling quick monetization of your data if it's data that you think is valid to share with others. And that is part of the Snowflake marketplace that you can access as a Snowflake customer. And of course, you can run build models, AI models, and deploy them into Snowflake and run them there. Snowflake supports Python R. Though I haven't seen any proper MLOps features in Snowflake, so that it has to be trained and MLOps has to be separated from the rest. Of course, Snowflake will deliver operational reports, ad hoc analysis, real-time analytics to your users on all the different use cases that you have there. Next contender up is Azure Synapse Analytics, or just Synapse, service formerly known as SQL's data warehouse. And Synapse is many different things bundled into one brand. But right now I'm going to be looking at the dedicated SQL pools or the SQL data warehouse part of it. And that is a SQL server that has been made massively parallel. Of course, the language that you're querying against is T-SQL. And the dedicated SQL pools are columnar per default. So it means that you have column store always on, but you can turn column store indexes off and use row-based indexes instead. Or of course, you can build non-clustered row indexes on top of your cluster columnar store indexes. It also has separate compute and storage, which means that you can pause the compute nodes and still have the database data stored. But it uses the same distributed database system that you find in Redshift. Which means that you have a controller node, which is when you are connecting to Synapse dedicated SQL pools. Typically, you can use Azure Data Studio or SQL Server Management Studio. And what you will be talking to is the controller node. The controller node then distributes the queries down into the different compute clusters. And underneath each compute cluster, you have either 3 or 6 copies of a SQL database. And again, that means that the data has to be distributed across these database copies. And you have to decide how to do that. And there are, here as well as with Redshift, there are 3 different ways of distributing data. You have your partition key. You can distribute all to one, or you can do a round robin. Synapse Analytics, of course, tries to build upon that cloud data warehouse and expand with bundling it together with the data factory, or what is now called Synapse pipelines. Big data processing with containerized Spark. Previously, we only had Databricks available. Now it's Azure Spark. Connected with your data lake. And of course, you have your massive SQL data warehouse solution that can query against the different data files that are in the data lake, both for ingestion and storing in a relational database, but also to query against external tables. And this is, of course, how they want to sell and market that, in that you have a one-stop place for all the different big data needs, and combine that with a nice workspace or Azure Studio, Synapse Studio on top of that, where all your users can sit and work. So again, Synapse is more than just your regular massively parallel relational database. It has serverless SQL pools, which means that you can build views and build tables and even data marts in SQL, queried against as a SQL table, but it will only be available when somebody hits or queries against that. Synapse will know which serverless SQL pool it is supposed to be querying against. And these are also insta stop and start, so they pause after 5 or 10 minutes or whatever you dedicate, but then they start again just as quickly as Snowflake does. However, the serverless SQL pools do not have cache in them right now. Synapse also comes with an improved Polybase version 2.0 that not only lets you create queries against your files in your data lake, but it also allows you to query against other SQL databases in your platform. You can query against Oracle, Teradata, and other on-prem sources as well, as they are external tables. I mentioned the containerized Spark, data factory, or Azure, Synapse pipelines, but it also is very, very tightly integrated with Power BI. And then again, everything in a single workspace that supports SQL, it supports R, it supports Python, Scala, Java, even .NET Spark language, where you can do everything you need on your data lake. Then we have BigQuery, and BigQuery is quite different from the others. It is serverless. It means you don't have to think about how to scale or how to start off with your clusters. You don't need to think about hardware at all. BigQuery will decide that for you when you run your query. So it scales up and down according to your queries, and you only pay for what you use. It is also based on ANSI SQL, like Snowflake. Since it's serverless, it's separate compute and storage. But as the others, it is also a columnar versus a row-based database. And it has a caching mechanism as well. That means that whenever you run a query that has been run before, you will hit the cache instead of hitting the compute nodes. And then the cost is nothing. So it's when you're hitting the cache, it's a free query. And yes, you pay per query and not for the capacity that you need. You don't need to think about that at all. You pay for the storage, which is a separate cost. And BigQuery is optimized for wide tables, which is important distinction from the others, which are more star schema optimized from a scale of Redshift and Synapse are all star schema optimized, whereas Snowflake is somewhere in between. And then BigQuery is wide table. It can run star schema as well, but it does perform a lot better on wide tables. And BigQuery supports ingesting data both live as well as batch ingestion. BigQuery also comes with something called Omni, which is a feature that allows you to run BigQuery on your data in Azure or your data in AWS by using the Google Anthos service, which is quite similar to Azure Arc, though it has been running for a while longer. It has been in service for a while longer than Azure Arc has. I would also like to mention Databricks Delta Lake, which is not one of the ones I'm comparing right now, but the Delta Lake and the Data Lakehouse approach from Databricks is quite interesting for those who are looking into different approaches than your traditional relational database system in solving your needs for your reporting. So, to look at the analysis of the systems. All opponents superficially resemble each other by using one version of SQL or another, where that is PostgreSQL or it's T-SQL or it's ANSI SQL. So it's very easy to start with, and it's easy to set up. And all of them allow for external data querying, so you have external table support. But only Synapse offers connections to other relational databases. With one exception is that BigQuery also has a connector to Google's own Cloud SQL database system. But Synapse is the only one that offers a quite wide package of relational database systems, as well as the blob store connection. On top of that, Redshift Spectrum also incurs an extra cost per query when you're running against the external tables. And all are scalable to a certain point. However, Redshift only offers 2 different scales per version. So you have small and large on DS2, small and large DC2, and small and large on RI3, which means that the scalability is quite limited, and it's not an auto-scale functionality in it. And again, BigQuery is not comparable because it's serverless. It scales up and down per query instead. And all the different competitors have support for external ETL tools, or if you want ELT tools. Redshift and Synapse SQL pools needs time decisions on distribution, because since they are distributed database systems, you typically want to approach data loading according to a strategy on, is it a staging table? So if it's a staging table, you typically want that only on one compute node and one database copy. And then you bulk load from there on and distribute it across the different nodes afterwards. If it's a dimensional table, you typically want to have a copy of each table on each node, because you want to have that as close as possible to the fact tables. And the fact tables are typically distributed across all the nodes according to one of these partitioning keys, whether that is year, or if it's customer key, or if it's something else, or if you just do it round robin. You typically then distribute the large fact tables so that each node has one slice of data. And that is why you want to have a copy of your your dimensional tables as close to all fact tables as possible. So you need to think about that kind of decision on Synapse SQL and Redshift. You do not need to think about that on BigQuery or Snowflake. BigQuery, however, you need to think about how to distribute your data to avoid joins. Again, I was mentioning that there is a performance increase on wide tables in BigQuery, and there's star schema table or systems perform a bit slower, but there is also a cost if you are running. It depends on which price point you pick on BigQuery, but the traditional one of paying for data being pushed through the system, as the more tables you join together in a query, the more data is being pushed through the query until you get the result. So redesigning your system so that you have more wide tables and avoid joins in your queries gives you a better cost option. So this is the design decision that you need to take as well. And these constraints are not on Snowflake. So this is a benefit of Snowflake. You don't have to think about design decisions on schemas, star schema, or wide tables or anything. It works. And all the different systems have browser-based query tools. Synapse also has the on-prem your local querying systems. And all of them offer APIs for external parties to connect to. But the workspace that Synapse has out of the box is the richest workspace for full development. Personally, after having worked a bit on Snowflake, I'm not a big fan of their interface, so I would rather go with a third-party connector to write code specifically for data engineering tasks in Snowflake. And one important feature that everyone looks at is speed. How fast are these systems? Which one is the best? And all of them, if you're looking at their marketing slides, all of them claim to be the fastest. So is it true? And it really depends, because you can tune your queries and tune your data in a way that your system performs in TPHC or TPH something else benchmark, so it performs best. So it is more up to how you use your data and how you use your systems, which one is the best fit for you. And typically, I would mention BigQuery as a big winner if you are already working on big tables. I had a talk with somebody at PASS Summit last year, and they had been hitting the wall on performance in Azure Synapse and in Oracle and Teradata because they were using wide tables. And BigQuery is a better option if you everything is aligned up to a big table system, because it is really, really fast and on wide tables, and it performs really well. But for more general data warehousing solutions with data lake and so on, how you tune it, how you hit the cache and so forth is what really depends for you. When it comes to availability, Synapse was just recently released into general availability. It's November 2020, and it is still in development. They're pushing out new features all the time. They are actually re-engineering their complete backend. I suspect we will see some release announcement on Microsoft Build in a short period of time. I think it's 2 weeks from now. But it's still in development. Snowflake is worldwide, and it is mature. However, as I mentioned, it is only available in certain data center regions. Redshift is also worldwide, but the RA3 version has been rolling out slowly. I'm not sure if it's completely worldwide yet, but it was very limited just a little while ago. BigQuery as well is also available worldwide, and it is mature and has been running for a while. RA3 was released January 2020, I think, into GA. And price-wise, Redshift has varying prices per version and then per tier. So it's and then as well the separate pricing for Spectrum. Snowflake prices storage per terabyte and then compute per second, and it's priced according to the node size at compute time. So it is a bit complicated to understand exactly how to calculate the cost, but it is possible actually, like certain Oracle licensing features, to understand how to calculate the prices in Snowflake as well. Now, Synapse has an auto scalability up and down on the SQL pools, serverless options, Spark cluster selection. So the price mix varies on what's the mix of services that you have in it, and can be a bit confusing at times to understand exactly how to price that, but that also is something that you will learn as you see your usage pattern. BigQuery, as I mentioned, it prices for storage, it prices for streaming inserts, and then the default option for pricing is per megabyte of data passed through the query at the query time. Though there are different versions of pricing that you can go in as well, which means you can pay per document, or you can pay for other more random, or sorry, not random, but pay as you go versions. And with all of these above, you can pay for a prefixed or say that you want to have 10 terabytes of data through the system per month. You can pay in advance for up to 3 years and get a discount of X%, I guess it's 40 or 50% or something, on the different services. That also includes BigQuery. You can pre-purchase capacity and get the discounts according to that. Other features that are worth mentioning is that the Azure Synapse links versus against Cosmos DB. The Synapse link might come into other features later on, but right now it's only available for Cosmos DB Analytical Store, which means that if you have your operational database system being Cosmos, you can avoid any kinds of separate third-party ETL tools and link your Synapse data warehouse directly into the Cosmos Analytical Store, which is columnar CDC loaded separate part of Cosmos, where data just trickles in. I think it's a buffer of 5 minutes or 10 minutes before it's available in the Analytical Store. And then it's queried against as a polybase connector within Synapse. Synapse also comes with Azure Synapse Pathway, which means that if you are running an Oracle appliance or a Teradata system, or you're running Snowflake right now, but you want to move to Synapse, they let you do that for free. It will also automatically translate the code, so your stored procedures and so forth can be automatically translated into T-SQL and be available for you in a lot less time than if you had to do that yourself manually. But none of these, even though Snowflake claims to be a data platform, none of these are real data platforms. Because in my opinion, to really get a proper data platform in place, to support self-service, to let your users trust your data, you need data governance and you need tools to support that. And out of the box, natively, AWS has Glue. And Glue is an ETL tool. So it's PySpark And if you are using Glue for your ETL into the different, whether it's Redshift or something else, it has a limited data catalog, but it's not that good. Azure has had, until recently, data catalog version 1, but it is quite shitty. Very poor, very basic features. None of these have a proper lineage or data quality tools or governance tools. But of course, you have the third-party tools available, such as Informatica or Colibra or Elation or somebody else. However, the preview features and the roadmap of Purview, which is Data Catalog version 2++, which was launched in public preview in November and is going into live sometime this summer, promises to be a game changer in that it enables you with Purview and with Synapse to have a full data platform with capabilities such as business glossary, metadata catalog, perhaps or hopefully even data quality going on that further down the line, but that is not something that is in the roadmap just yet. But the end-to-end Azure strategy seems to be to build a proper data platform on top of Synapse. So in my opinion, Synapse as an end-to-end data platform is really selling point. That with the common workspace is for me really positive. However, if you're not fond of the different components and having to control all the different parts of the Synapse platform, Snowflake is a really good contender. It is out of the box, really fast, it's easy to work with, running with extra tools such as 5chan or Matillion to ETL it, and then use DBT for DevOps or DataOps integration of your source code, and Snowflake for everything else is a really good match. BigQuery is a contender, serious contender in certain features, though all in all, I'd still say that because it is running on Google and Google, unless you do have everything else on Google, it is a third contender or third place in this part. Whereas AWS, in my opinion, does not have anything that lets it stand out against its competitors in any way at all, apart from it being on AWS, of course. And that is my verdict for this. So, with 6 minutes to spare, are there any questions? Howard? So I see there's a question from Adam. What about CI/CD capabilities using different dev test prod environments? Yeah, as I mentioned a bit with Snowflake needs to have different tooling in place. So DBT is typically the most common tool to use, either with 5chan to CDC data in or Matillion for transformation data in. But you need third-party tools to get proper CI/CD functionality on it. And in Snowflake, you need to, everything is actually bundled in together, so you need to use a dedicated warehouse and so on. So it's not really prod environment friendly in that way. Synapse is on its way there. It has a source control integration right now. So you can integrate with GitHub and with Azure DevOps, but it is not quite mature yet. Hopefully it will get there, but from the data tooling that is bundled into Azure already, it is quite CI/CD friendly. And in best practice with Microsoft, using different subscriptions as different environments for dev test prod is quite easy to set up, but it is something that you set up from a subscription point of view rather than a resource group or so on that you did before. BigQuery as well, you can have, because it is serverless, you can typically have several BigQuery nodes or endpoints you connect to with data lakes underneath. that serves the different environments that you have. And Redshift, because Redshift is dedicated capacity much more than the others, you will need to have I think it's the least friendly in that aspect compared to the others. And CI/CD, I haven't really tried on Redshift. I did on the others. So, but all in all, that's my approach. I would say Synapse, Snowflake, Google, and then Redshift in that order. Delta Lake, the Lakehouse, yes, it fits in there somehow. You might see Delta Lake being open sourced. That might actually be supported in Synapse as well later on. At least it says so on the. I think it's right now it's available for Spark. I would suspect it comes from other parts of Synapse Spark. It probably will be available other places as well. But yes, it is a valid contender. I really do like the Delta Lake format as part of a wider data platform approach. If SQL pools in Synapse could support the Delta Lake format, you could have an end-to-end virtual or logical data warehouse where Delta Lake tables is your baseline, and then you decide where you want to serve it afterwards. Personally, the Lakehouse part, I think it's more of a marketing language than anything else, but it seems to have hit a lot of people well. But you get that same functionality with the others already, in my opinion. Though if you look at Databricks, their definition of the data lakehouse is either Databricks or it is Azure Synapse. That's actually mentioned on their webpage. Any other questions? Yeah, all the different systems support streaming data in. Of course, in my opinion, the Synapse SQL pools, which I've tried, and the same goes for Redshift, struggles with real-time inserts of data. But that's where you will get either Spark or the serverless SQL as endpoints instead. Whereas Snowflake handles inserting of stream data quite well, unless you start, if you are using Snowflake or the Snowpipe part of Snowflake to pull data from an event hub, and instead of having somebody push data streaming into Snowflake, it doesn't work. You will need to have either Stream Analytics or Kafka streaming or Storm to push data actively into Snowflake. That handles that really well. BigQuery also handles streaming data inserts really well without any problems. So depending on your architecture, either if you just have to have or want to have one single system, I would say Snowflake or BigQuery are the best for streaming data. If you're okay with having different components in your architecture to handle different services, Synapse is also a valid approach for that. But of course, it depends on how you want to use that data stream afterwards. Do you need to have that going through your database and out into reports real time, or can you do streaming into real-time reports when live data is really needed, and then do inserts into database and then batch analysis on that data stream afterwards? So it depends on your use case exactly. Okay, seems I'm on time now anyways, so not to distract the next speaker, which I think will be a Snowflake session. If you have any question later on, I will be online during the Q&A session at 6 p.m. So you can always feel free to talk there, or you can reach out to me on Twitter on the handle Intolerance, or look me up on LinkedIn. Otherwise, thank you so much for your attention, and have a nice conference for the rest of the period. Thank you.